Okay, so we are on chapter 2, and that is physical biochemistry. So we really have three big sections in this chapter. The first one is all about energy conversion. So we call energy conversion, we call this bioenergetics. And that's a big part of this chapter. Then we're going to talk about water and why it is so important for all living things, and all about its really non-covalent interactions. And then we're going to talk about cell membranes and how they function and why they're so important. Maybe if I could advance to the next slide, that'd be good. All right, so energy conversion, that's the first one we're going to talk about, bioenergetics, right? So we see bioenergetics in, for example, the transformation of solar energy into chemical energy in plants, right? And we also see it in the interconversion of chemical energy. So through oxidation and reduction of molecules. And so you see it in a lot of different places. And in order to understand it, we have to understand the principles that underlie energy conversion in all living systems. And so those are the laws of thermodynamics. And so we're going to go over all of those today. And we're going to talk about exergonic and endergonic reactions, right? And ones that require energy and ones that give off energy, and how they're coupled. And we're going to talk about the adenylate system. So adenylate, ATP, AMP, ADP, right? All of those molecules. And how they manage all of the short-term energy needs inside of the cell, which is super interesting. Okay, so bioenergetics is defined as energy conversion in a biological system. We see it, like I said, we see it in photosynthesis, where we transform solar energy into chemical energy. But we also see it when we do our interconversions in a redox reaction. So redox, shorthand for oxidation reduction, which y'all should already know. So why is chemical energy important? Well, chemical energy is what organisms use to do things. And I'm not just talking about walking around and that kind of thing, but I'm talking about inside the cell. It has to do all kinds of different functions. And so it uses chemical energy to do that. So it's essential for cell survival. And usually we get them from the environment, right? So plants can use carbon dioxide and carbon fixation to form carbohydrates. And so they use light energy, right, to fuel everything. But then what happens at night? Well, they have to form carbohydrates, and those carbohydrates are then broken down and serve as their metabolic fuel during the night, which is exactly what happens in us all the time because we're non-photosynthetic. So we just eat the carbohydrates that the plants make, or other biomolecules, right? And we use it as our metabolic fuel for anaerobic respiration, right? So what we do, plants also do just at night. So what kinds of work can a cell do? Well, there are three things that a cell needs to be able to do, and it needs to maintain osmotic pressure, and we need to worry about maintaining certain concentrations of solutes on one side of a membrane versus another side of the membrane. We need to worry about making and breaking down organic molecules. Some things we need to make, some things we need to break down. Either way, a lot of times they require energy. And then you actually have to have mechanicals. This is probably what you're thinking of when you think of work. And for example, that is muscle contraction in animals. And we're actually going to talk about that one as well. So what are different kinds of energy, right? Well, if you really think about it, inside of the sun, right, hydrogen is being converted to helium in a thermonuclear fusion event, right? And that's giving off electromagnetic radiation in the form of visible light, right? And so that's what solar energy is. And so then we have plants that are taking that solar energy and using photosynthesis and creating chemical energy. So we can then take that chemical energy that the plants have made, and we can do osmotic work, we can do chemical work, and we can do mechanical work. Okay, so we're going to talk about each of those different ones. So why do we have to do this work? Well, the big reason is that we have to maintain homeostasis. Homeostasis is super, super important. If you're not maintaining homeostasis, you're dead. So it's a highly ordered steady state in terms of temperature, in terms of concentration of biomolecules, right? And it's really important to note that what our cells are maintaining as homeostasis is not equilibrium. So homeostasis is not equilibrium, right? So when our cells die, then they go to an equilibrium state, right? And the macromolecules will equilibrate to their surroundings. So our whole life, we're requiring energy to delay this equilibrium event from occurring. So homeostasis occurs in living things, equilibrium occurs in non-living things, right? So it's the fundamental reason why all organisms need input of energy to delay that conversion from homeostasis to equilibrium, right? Okay, so redox reactions. This is how we're going to make this chemical energy work for us. In redox reactions, remember that we have electrons that are transferred, right, from a molecule of higher electrochemical, CTRO chemical. You don't need to spell to get a PhD. It's a good thing. Okay, so you're transferring your electron from a higher electrochemical potential to one of lower potential, right? And so you see this in photosynthetic organisms, right? Photosynthetic organisms are using solar energy, right? They use solar energy to oxidize H2O, right? And then they produce O2 from that. They can also generate chemical energy. So they can generate sugar, C6H12O6, right? And so that's what they use at night to sustain themselves. So all of these oxidation reduction reactions are used where chemical work needs to be performed, okay? So here's kind of an example, right? Remember, reduction versus oxidation. This is one that you should already know this. And remember that electrons aren't free, right? They don't exist in solution. So a reduced compound becomes oxidized only when it transfers that electron to an oxidized compound. And then when that oxidized compound picks up that electron, it becomes reduced. So you got to remember, you never have free electrons floating around. You're just transferring electrons from one place to another, right? So the example you see at the bottom, right? We're talking about aerobic, A-R-E-O-B, aerobic respiration, right? Please don't make me spell things, right? So what you can see are electrons get transferred, right, from the sugar. And then we're moving them to other compounds, right? So here we see our electrons are moving, and then we're releasing carbon dioxide. So this is an oxidation reaction, right? We're going from our sugar that's losing hydrogens, that's losing electrons, and we're increasing the number of oxygen to carbon, right? So the absorption of those electrons, that transfer of those electrons is changing you from reduction to oxidation, right? And so if you think about how this works in plants, right? Plants have that pigment, they have that chlorophyll, right? So this is photooxidation of the pigment chlorophyll. And so when you have that photooxidation, the light hits the chlorophyll, right? And the electrons move from the chlorophyll and they move to an acceptor molecule. When it moves to that acceptor molecule, that's a molecule that has a lower electrochemical potential. And then they keep moving and keep moving, right? And so in the end, what are you trying to do? You're trying to synthesize an energy carrying molecule. And in this case, we're synthesizing ATP. And we're going to talk a lot more about ATP shortly. So to understand better how energy is used inside of a biological system, we kind of need to review some really, really basic thermodynamic principles. And you really should know all this. This is like first year chemistry, right? So system, collection of matter in a defined space. Like anything we choose, it's the reaction that's going on inside of a test tube, or the gas inside of a balloon, or whatever it is. And then the surroundings are all the space that are not included in the system. And then, though your book doesn't say it, the system plus the surroundings gives you the universe, right? And so sometimes when you think in chemistry terms, you're thinking of a test tube, right? But you also have to think about biological terms, and you have to think it's a living cell. It's an entire cell. It's everything that's going on inside that cell. Or maybe even it's an entire organism, right? So there are three different kinds of systems. There are open systems, where you have an exchange of matter and energy between the system and the surroundings. You can have a closed, where you only have energy exchanged with the surroundings, right? And then you can have isolated, where neither matter nor energy is exchanged. And what you're going to see is biological systems are always open. So these are biological, right? Biological systems, because we have matter like nutrients and waste that get exchanged. And then we have energy, heat, that's exchanged with the environment. So it's definitely an open system. So let's talk about our different laws of thermodynamics, right? So biochemists use two main laws of thermodynamics in order to describe biological processes. So the first and second law. So the first law, right? The first law, we say the total amount of energy in the universe is constant. It's not going to change. So another way to say that is that energy is neither created nor destroyed, right? Energy can only be converted from one form to another. You can't create it. It would be super cool, but you can't do it, right? So we know that our change in energy is the difference between the final minus the initial. But what is energy, right? Energy is also equal to Q minus W, right? So our energy change is equal to the difference here between the heat, that's Q, transferred into the system from the surroundings, and W, which is the work done by the system on the surroundings. So most of our energy conversions in the physical world involve changes in pressure and volume, right? If you're thinking in basic chemistry. But in a living cell, you can't change pressure and volume. So you have to convert energy in a condition where your pressure and volume are constant, right? So to measure the energy change in a system, a biological system, we need to talk about enthalpy, right? That's H. Ooh, uh-oh. I want to keep them. Okay. Oh. Y'all bear with me. Okay, here we go. Now back on track. Try not to do that again, Dr. B, right? Okay, so what was I saying? Oh, we can't change pressure and volume in a biological system. So what are we really worried about? We're really worried about heat, enthalpy, right? So we know that, right? H is equal to energy plus pressure times volume. Okay, so we don't know absolute values, but what we do know is the change in, so that we can actually measure when we have different conditions. So if we combine these, right, delta E is equal to delta H minus our change in pressure times volume, right? But another way to say that is also Q minus W. Well, we know that this is basically going to be 0 right here. And we also know that our work here is 0. So we can combine this and say delta E is equal to delta H minus 0, which is equal to Q minus 0, right? So then when we simplify, delta E is equal to delta H, which is equal to Q, right? So this is kind of just biological systems if you're taking into account no change in pressure or volume. Okay, so our second law. Our second law says, in the absence of energy input, all of our spontaneous processes in the universe tend towards the dispersal of energy. Disorder, you probably heard it that way before. And the measure of the disorder is always increasing in the universe. So the universe is always tending towards disorder. So if you look at our disorder, so that's S, right? What's important to remember is that all biological energy conversion processes are not 100% efficient. So when you're doing these energy conversions, you're losing energy to heat, right? It's not all being used for work. So you have to think about what's going to happen to give off heat as well. So we're going to talk about both of these laws kind of together. So if you look at a reaction, there are two kinds of reactions. We have endothermic and we have exothermic, right? So in endothermic, our reaction is releasing heat and it gives us a negative delta H value. So if you've ever used those hot hands, I tell you, I used them when I lived in Iowa relatively often because it was really cold. and so you mix the chemicals on the inside of the packet and it warms the packet and you keep it in your hands and it keeps your hands very, very. Endothermic reactions, on the other hand, will absorb heat, right? That has a positive delta H. So for example, you want to keep your body heat warm during the cold winter, so you put a coat on. So you're actually absorbing heat. Entropy, on the other hand, is a measure of disorder. So think about, when you think about a biological system, really you should think about energy due to motion. So disorder, so really energy due to motion, right? So it increases when there is more dispersal of energy in a system. So if you have some really, really big biomolecules and you start breaking them down into smaller and smaller molecules, you're going to end up with more movement, more energy, and so that's a dispersal of that energy. So degradation from large to small, we go from large biomolecules will have a high S, these will have, oh, I did that wrong. These will have a low disorder, these will have a high disorder, right? So when you want to know if a reaction is going to be spontaneous or not, right? Just because you know how much potential energy is inside of those bonds when you're calculating delta H, it doesn't tell you that the reaction is going to be favorable. So in order to know if a reaction is going to be favorable, you have to take into account delta H and delta S. So enthalpy and entropy. So you have to be careful about that. You're looking at all different parts of the system. So let's take an example of entropy. So, right, delta S, right? Energy due to motion. If you look at water, if you're in the solid state, right, those molecules, these water molecules inside of our solid phase ice are locked in a particular arrangement. They're not moving very much at all. So they have very low motional energy. When you convert from a liquid, from a solid to a liquid, what's happening is now those molecules can move around. And so the bonds that are between those molecules are going to fluctuate. They're going to be made and they're going to overcome, made and overcome, made and overcome, made and overcome. And so you're going to have lots and lots of movement. And so this is why if you leave ice out, it will melt. You don't have to put energy in for it to happen. It's spontaneous. So you need to think about enthalpy, delta H, and you need to think about entropy. But we know entropy really dominates. So that's what we're going to kind of focus on, right? So melting of water is entropically favorable because we have a dispersal of energy in liquid than we do in ice. So when we go from a solid to a liquid, right, our delta S will increase. And so that's why it's spontaneous, right? So, right. So how do we know that a reaction is going to actually happen? We have to calculate Gibbs free energy. Gibbs free energy is the difference between the enthalpy and the entropy of a system at a particular given temperature. But the thing is, we really can't measure these absolute values. So instead of looking at absolute values, we're going to look at the change in each of these values when we have two different conditions, right? And so if you think about other, let's see, I'm trying to think about other examples of this in a biological system. If you think about the flow of ions from a channel, inside of a channel. So you have a membrane, right? And you have the channel, and you have your ions moving from an area of like high concentration on the outside to low concentration on the inside, right? What are you doing? You're changing the entropy of the system, right? And so this is why we have action potentials inside of our cells. So when we talk about this, we're going to call these biological reactions exergonic or endergonic, right? So we're looking at Gibbs free energy. If Gibbs free energy is less than 1, we're going to favor going in the forward direction. Whichever way your reaction is written, it's going to progress in the forward reaction. So the reaction is overall favorable and it's spontaneous. Endergonic goes the other way. So this is seen in reverse reactions. You would write out the reaction, and whatever way the arrow is pointing, then the opposite would be favorable, right? And so it would be non-spontaneous reactions. So you have to be able to compare these, but in order to compare them, you have to have a defined set of conditions. So we call it standard free energy change, delta G naught, and that's this little circle right there. And so our standard conditions are constant pressure of 1 atm, room temperature of 298 Kelvin. We're going to stay in Kelvin. And it's important to stay in Kelvin in these calculations so you don't have a negative sign there. We get really crazy. And then our reactants and our products are both at the same concentration of 1 molar. So delta G naught is a constant for a given reaction. But be careful, there's also a biochemical standard, right? And so that biochemical standard, we put an extra little symbol right there, right? We put a little extra notation. And so our biochemical standards also include being at pH 7, having a concentration of water at 55.5 molar. And if you have magnesium present, your magnesium concentration should be 1 millimolar, right? And so when we're looking at biological reactions, or any reactions really, you have 4 possibilities. The reactions could be completely spontaneous all the time. So they're completely independent of temperature. They could never be spontaneous. Doesn't matter how hot or how cold you get, it's never gonna be spontaneous. Or it could be spontaneous at a high temperature only, or spontaneous at a low temperature only. And so your book has a little table there that tells you, if you have to go back, you have to remember your formula here, right? Delta G is equal to delta H minus T delta S. So what's going to happen? So if the sign on delta H is negative, right? And the sign on delta S is positive, then what's the sign of delta G going to be? Well, if I look at this, I know that I have a negative here minus T is in Kelvin, so temperature is always going to be positive. So really you have to look, you have a negative in front of a positive times another positive. So if you put all that together, you're going to end up with a negative number. So you have 2 negatives, a negative, like a negative plus a negative. To get delta G is going to be negative. So that's spontaneous. So it doesn't matter what temperature this reaction is going to be at. If you have a negative delta H and a positive delta S, you're going to have a spontaneous reaction. So if delta G is negative, it's going to be spontaneous, and it's going to be spontaneous at all temperatures. So your book has this table, but for me, as long as you understand delta G is equal to negative delta H minus T delta S, if you can write that equation, you can figure out, okay, what happens if delta H is negative? What happens if delta S is positive? And vice versa. So you really only have 4 different ways to think about it. So this is not what your book does, but this is the way I think about it, right? So we already did this one where we have an exothermic reaction with a high delta S. So we said that our delta H was negative. We said that our delta S is going to be positive. And so we end up with a negative value there for delta H and a negative value for this T delta S, right? And so you're always going to get a negative G, delta G. So this is always spontaneous. So you can do that for another kind of exothermic reaction, but on this hand has a low delta S. So if it's low, we're going to assume it's negative, right? So our delta H is the same because it's exothermic. It's going to be negative. And then we're going to look, right? We have a negative in front, and we're going to multiply that times temperature. Temperature is going to be positive. And in this case, we're saying we have low entropy. So delta S is going to be negative. So a negative times a negative gives you a positive for that cluster of values there. So a negative plus a positive. Well, here it gets tricky, right? The only way you're going to get a negative delta G is at really low temperatures. Because if your temperature is low, this positive value is going to get smaller and smaller and smaller, and so you have a more likely chance of delta G being negative, right? And I'll show you one more, and you can just, if you logically think this out, you don't have to memorize anything. So what if both terms are positive? So what if you have an endothermic reaction with really low disorder, with really low entropy? So what you're going to see is that delta H is going to end up being positive, and then that delta S is going to be negative. So you're going to have a negative for this value right here. You have a negative, temperature is going to be a positive, and then delta S is going to be a negative. So a negative times a negative gives you a positive. Well, if you have a positive and a positive value, there is absolutely no way that you can get a negative delta G value. So this will never be spontaneous. Doesn't matter how hot, how cold it is, never spontaneous. So if you understand the relationship, you can figure all of that out. So, all right. So now let's talk about our relationship between free energy and equilibrium, because that's kind of 2 really important things that we have to worry about in biological systems, right? So the magnitude of the standard Gibbs free energy is really a measure of how far the standard state is from equilibrium, how far we are away from that equilibrium. So this is I call this the Ratlink equation, right? So delta G is equal to negative RT ln of K, right? So when you do this, right, R, don't forget, is your gas constant, because there's 2 different R's, right, of 8.314 joules per mole K, right? And T is going to be absolute temperature, okay? So we're looking at the standard reaction. A plus B goes to C plus D. So we can write an equilibrium expression for that. Products over reactants, right? And then we can look at the value of K equilibrium. If it's less than 1, we're going to favor formation of the reactants. So that's if K is less than 1, right? If K is greater than 1, then we're going to favor formation of the products, right? Because remember, it's K is products over reactants. So if K of equilibrium is greater than 1, what is that telling you? That's telling you that you have more products than reactants, and so you're going to shift in that direction, right? But what happens if K of equilibrium equals to 1? That tells you that the reaction's at equilibrium, right? So really, K is the measure of the directionality of the reaction at standard conditions. So is it going to be favored forward, or is it going to be favored reverse? So most biological systems are not at standard conditions. They're not. So if you want the actual free energy change, you're going to have to do delta G is equal to, that's the real, the actual free energy, is your standard state, right? Plus RT ln of Q, not at equilibrium. K is at equilibrium. Q is basically initial concentrations. It's whatever concentrations you are. So Q is very similar to K. It's the wannabe K, right? It's your products, your initial concentration of your products over the initial concentration of your reactants, okay? So if the equilibrium, if the reaction is at equilibrium, right, then that's telling me, I don't know, I'm running out of room over here. Then that's telling me that Q is equal to K, right? If we're at equilibrium, Q is equal to K. And it's also saying that delta G must be equal to 0, right? So if we put that into our equation, we know delta G is equal to our standard plus RT ln of Q, right? But if we just said we're at equilibrium, right? So that's telling us now delta G is equal to 0. So then we have our standard state plus RT ln. In this case, Q is equal to K. So I can put KEQ. So then I rearrange and I get standard minus RT ln of K equilibrium, right? So if our delta G, in this case now, is less than 0, then we're going to shift from the left to the right. And vice versa. If delta G is greater than 0, then we're going to shift from the right to the left. Okay? So the actual reaction inside of the cell can be favorable, where you have delta G that's less than 0, even if the standard delta G naught is unfavorable, right? Because you have different concentrations in initial or current conditions versus equilibrium. So just kind of keep that in mind. All right. So like we said, most biological systems are not at standard conditions. I kind of just already did this. I guess I didn't really have to write that. I forgot I had all that in there. So we talked about our actual free energy, and I already derived all this for you, so I'm just going to leave it. All right. So then we said our biological standard conditions, right? We have to add those 3, pH 7, concentration of OH, and concentration of magnesium ion. All right. So how can unfavorable reactions, endergonic reactions, occur in living systems? If it requires energy, it's not favorable. Why is it going to happen? Well, we're going to couple reactions. So we're going to take an unfavorable reaction and couple it to a favorable reaction. And so ATP hydrolysis is a common coupling reaction. It is favorable. It has a delta G of minus 30.5 kilojoules per mole. So it's great, but here's the thing. If you're going to couple reactions, you have to add the free energies of the separate reactions to find the overall. But this only works, only works if the two reactions share an intermediate. And I'm going to show you what I mean when I say they share an intermediate. And the other way, it's also possible for ATP to induce a conformational change, and I'm going to show you that as well. But first, we're going to couple and look at overall delta G. All right. So in a standard reaction, right, we have A plus B goes to C. C is our intermediate because C is going to be a reactant in reaction 2, and we're going to convert it to E, right? So this works because C is converted to E in the presence of D, right? So why does the coupling reaction work? You can look at the delta G's and you can add them up and you can see, okay, mathematically, when I add my delta G's for the two reactions, I'm going to get an overall favorable reaction to occur. But why? So if you have D present, it is going to use up C to make E. So basically what you're doing is you're decreasing your concentration of your product in the first reaction. So what happens to that reaction? That reaction is going to shift towards the products. And so it's going to make that initial reaction more favorable, even though it requires energy to do. So C is used up in the equilibrium reaction, and so that first reaction is going to shift to replace the C. So it's kind of a cool thing. So when you look at ATP, right? ATP hydrolysis is the coupled reaction that gives off energy that we really, really like to use in the cell. And so you can see that there are two different places where you're going to get a lot of energy from cleaving this molecule. You can look at, this is the alpha phosphate, here's the beta phosphate, and here's the gamma phosphate. So if you hydrolyze between the oxygen and the gamma, what you're going to get is a delta G of minus 30.5. If you cleave between the beta phosphate and the oxygen, you're going to get 32.3 kilojoules per mole released, right? So it's not really the cleavage of the phosphoanhydride bonds that's going to drive reactions and provide that energy. It's actually the transfer of either the phosphoryl adenylate, so AMP, to a reactant, AMP plus a reactant, right, to generate a highly reactive intermediate. And that's what's going to give you the energy push to make it happen, right? So if we look, right, here's an example. Here's an example of this. We have glutamate. Glutamate, we're going to add NH4 plus, and we're going to get to glutamine. But that's an unfavorable reaction. So what we do is we couple it to ATP hydrolysis. So what happens is, if you look here at the glutamate right here, right, we're going to take the phosphate group right there and attach it to the glutamate. And when we do that, now we have this very high energy intermediate. Oh, we have an intermediate. Yes, okay. And now we can then make the product we want with glutamate synthase, and we're going to release our inorganic phosphate. And so you're going to have a release of our ADP, a release of our inorganic phosphate, and then we can keep reusing our ATP, our AMP, our ADP, and our PIs, so that we can continue to use these molecules to drive reactions. So the other way that we said that that ATP can be used to drive reactions, right, is to where ATP will bind to a protein. And I'm giving you two different examples here. So here's ATP. ATP is going to bind to the protein myosin. Myosin's a motor protein. So myosin can bind to like a vesicle, and it can attach to the actin cytoskeleton. And so what happens is, you think about like the actin polymer there as like rope. And the myosin has an arm on it, right? And so it can hook on to the actin. And then when ATP binds it, right, the ATP can hydrolyze, and that hydrolysis basically cranks the motor of the myosin, the head group of the myosin, and ratchets and pulls the actin, right? Let's go, resets, binds another ATP, hydrolyzes that ATP, and ratchets again. And so it pulls the rope of the actin polymer. And so it's the conformational change in myosin due to the hydrolysis of the inorganic phosphate from the ATP that drives muscle contraction and transport of vesicles across a cell and all that kinds of stuff. The second way is you can have, in the second case down here, a transport molecule, a transport protein, right? And so when it binds ATP, if it's an ATPase, right, the change in conformation due to the cleavage of the inorganic phosphate from the ATP will induce a conformational change, and then it will drive ions from one side of the membrane to the other side of the membrane, and vice versa. So this is conformational changes, whereas before it was energetic. Okay, so now let's talk about the energy. This is kind of cool, the energy charge of the cell. So the relationship between ATP, ADP, and AMP at any one time in the cell is called the energy charge. And it takes into account all the numbers of those phosphoanhydride bonds that are available for work. And if you think about it, right? If you think about it, somebody weighs 70 kilograms, because we're going to think in metric because we're scientists, right? We're scientists. But I'll tell you, that's about 154 kilograms, right? It's about 154 kilograms. If you were 154 pounds, oh my God, pounds. I just want to stay in metrics so bad. You're gonna need approximately 100 moles of ATP per day. 100 moles of ATP. So if ATP is 507 grams per mole, how many grams of ATP do you need? So it's 100 moles of ATP, right? If you have 507 grams per 1 mole, right? Then you convert that from grams, 1,000 grams, and 1 kilogram. What you would end up with is about 50 kilograms of ATP per day. And I know kilograms, right? 110 pounds of ATP per day that you would have to hydrolyze. You would have to consume that much. We can't do that. So what we have to do is we have to recycle. Our bodies are really good at recycling ATP within the system. And so this regulation of the energy charge is regulated by a metabolic flux. And so you can't consume that much. You can't. So we're going to have to recycle. So let me show you what that looks like. So this is the different energy molecules within the cell. And so here's our physiological range. We need relatively a lot of ATP, right? We have lower amounts of both AMP and ADP. And so think about this. How does this work? Did I put in this? Yes, I did. Okay. So how does this work? Your book kind of goes into it, but you take AMP, and that's in monophosphate, right? Mono means one phosphate. And you add ATP to it. And from that, you're going to generate 2 ATP. Because if you think about this, this has 1 phosphate, right? This has 3 phosphate. And so what you did was then you just moved 1 phosphate over. So now you have 2 molecules of ADP, right? Plus ADP. And they each have 2 phosphate groups on there, right? Now that you have these 2 ATP, you can take some of these inorganic phosphates that are floating around and you can convert that to ATP using ATP synthase. So you use 1 ATP and you get out 2 ATP in the end, right? But this is your net reaction. So you're going to do that all the time, all the time. So the other thing that your body has to be able to do is catabolic pathways. We have to be able to convert energy-rich compounds into energy-depleted compounds, so like waste. And so when we do this, our energy charge is low, right? So think about heterotrophs. What do we use as our energy-rich compounds? We use carbs, we use lipids, we use proteins, right? We use all of those to get our ATP. So we're going to generate ATP. So our energy charge is low. We're going to convert those energy-rich compounds into energy-depleted compounds, and from that generate ATP and reduce coenzymes, NADH, NADPH, FADH2, right? All of these storage molecules. So then these storage molecules are used in biosynthesis. So they can be used in biosynthesis, E-S-I-S, synthesis, right? In all kinds of anabolic pathways. Those are anabolic, right? Catabolic is breakdown, anabolic is build, right? So if you think about the energy charge of the cell, right? If the energy charge of the cell is equal to 0.5, what that is telling us is that our concentration of all three molecules is equal, right? But is that really what we want? We don't really want them to all be equal. What we said is that the common energy charge of the cell is anywhere between 0.7 to 0.9. So what we have is an excess of ATP. That's why we are between 0.7 and 0.9, right? All right, so anabiotic pathways. These produce biochemical molecules from smaller molecules. So this you're going to do when the energy charge is high, right? And we're going to use that ATP to replenish stored fuels so that we can actually do things. And so we have a balance between catabolism and anabolism inside of the cell. And so they're constantly balanced and going back and forth, right? To getting that fuel, eating that fuel, converting that fuel. And so you have to remember that it is always, always, always balanced. Okay, I think, oh no, we have one more. Okay, enzyme regulation mechanism. You have to regulate this. You have to have a way to slow catabolism, to increase anabolism, to have a balance inside of the cell, because you're not always at constant conditions, right? Think about how you feel when you've gone without eating for a while, right? You're very, very hungry. Your cells can tell that, right? And so how do you regulate enzymes that control catabolism and anabolism, right? And so some things that you can do is you can put covalent modifications on those enzymes. You can phosphorylate them, you can adenylate them, you can put an acetyl group on them, right? So you can add things to it. That's the covalent modification. You can have an interaction of that enzyme with something else that's going to change the conformation of the protein, either to make it more active or to make it less active. It could go either way. So both of these are examples of protein modification. One, you're covalently modifying, and the other, you're changing the conformation due to binding of regulatory molecules. Both are very, very common. The last one is where you actually sequester. So you compartmentalize the enzymes within the cell. And so by sequestering them, you can alter the rate of either synthesis or degradation of the proteins. And so that's another way to regulate. Okay, that is the end of 2.1. All right, let's see if I can pause this.